Hey, Mr. Allred, I want to talk about integration by parts. And I want to get to tabular integration, but the integration by parts formula is up here. It's if you have an integral of two things multiplied together, and we call it or label it u dv. Integration by parts says the integral of that is u times v minus the integration of v du. And this can be a long process or a short process depending on what you're dealing with. So I want to start working through the integral of x cubed sine x dx using this formula. And I probably won't do it all the way because it's rather long if we use this formula. But I wanted to get to a point where I could show you tabular integration. So let's see here. These two things are multiplied together, and you can't use u substitution because one is not the derivative of the other. So if you're going to pick a u, you want something that's easy to take the derivative of, which could be x cubed, and the dv will be sine x dx. So derivative of u, du would be 3x squared dx. And the integral of dv would be v equals, and the integral of the sine is negative cosine of x. So we integrated the dv and we took the derivative of u. So in putting that back together, this will equal u times v, which will be, if I look at them right here, negative x cubed cosine of x, and then it will be minus the integral of v du, which we have a negative cosine, so we're just going to go ahead and make that positive out front, but then it will be 3x squared cosine x dx. So we've got something that's already integrated. Let's see if I can get some more colors here. Ooh, that wouldn't look good, green on green. But the negative x cubed cosine of x, and that doesn't look good either. Let's pick a different color. Let's see. It's already integrated, so we're going to keep it. But the plus integral of 3x squared cosine x dx has not been integrated. So we would have to do the same process again. So over here in doing this part, we could say u is 3x squared and dv is cosine x dx. So derivative of u would be 6x, and the integration of dv would be sine x. Sorry, I left the dx off over here. So now we would have plus this new u dv, so 3x squared sine x, and now it will be minus the integral of v du. I should have called that du instead of u prime. Habits. But that will give me 6x sine x dx. And I have to repeat the process again. So if I have a high power there and I'm using the power rule to try and eventually get this thing away, it's going to take forever. Okay, not forever, but you understand what I'm saying. So let me show you how tabular integration works. Let's see if I can make this happen. And maybe you can compare it with what we've already got. So let's write down what we've got. We want to take the integral of x cubed times the sine of x dx. So I'm still going to, in the beginning, decide what my u should be and what my dv should be. So as far as my u goes, I will use x cubed, and as far as my dv, I will use the sine of x dx. Now I'm going to make a table here, and I'm going to take the derivative of every u. So down the line here, I took the derivative of what I called u for du, and then when I got over here a little bit later, I did the same thing. I have a new u, and I took the derivative of it. So let's see if I can keep a straight line here. But the derivative of x cubed is 3x squared. Okay. I'm going to continue that until it goes to 0 because it's a polynomial and it will disappear. Derivative of 3x squared is 6x. Derivative of 6x is 6. And then the derivative of 6 is 0. Okay. Now on the opposite side, I have dv, and I was integrating dv to get v. And as long as I keep the same part of the function as far as the part I'm integrating, I'm going to do the same thing here. So I got to be careful and make sure it's neat. But the integral of sine will be negative cosine of x. And then I'm going to integrate that again, which will be negative sine of x. Integrate that again, it'll be positive cosine of x. And integrate again, it will be a positive sine x, I believe. And you can follow this up backwards. Derivative of sine is cosine, derivative of cosine is negative sine, derivative of sine is cosine, but the negative follows. Derivative of cosine is sine with a negative, so I change the sign. Okay, so I've got these two columns. What I'm going to do is I'm going to take the diagonals. Okay, because the diagonals are a v and a u. Okay, so the original was a u, and I had to integrate one time to get to v. So this is the part I was keeping up top, uv. So I'm going to take every one of these diagonals until it runs out. Okay, and if you remember in the equation up top, we had a negative in between. We had a negative between the part that was integrated and the part that still needed to be integrated. And if you keep applying negatives, it kind of flips the sign. So the first part is going to be positive, then the next one will be negative, then positive, then negative until it runs out. And whatever signs are there, we will keep. But this integration turns out to be all of these things added together, and we can at least feel good about it if we look at the parts we have. But we should end up with negative x cubed cosine of x, and then we will have negative negative, which will be positive 3x squared sine of x. So I'm just writing out these diagonals. And then I will have plus 6x cosine of x, and then the next one will be minus 6 sine of x, and then I start running into zeros, and I don't need them. So if this is an indefinite integral, we would definitely put a plus c at the end, but let's see if we at least got what we had. So the two things that we did come up with above was the negative x cubed cosine of x, which we've got, and we also came up, even though I didn't highlight the original time, plus 3x squared sine x, which I have here. And then if I continued on with the other process, I would get this over here, but the table is much, much quicker. Okay? So the key here is to, if you have something that you can take the derivative of enough times and it goes to 0, that will stop the process. But you do have to have two things, one that you can take the derivative of over and over, and the other one you can integrate over and over. So derivatives are okay because we can take the derivatives about anything, but integrals are a lot harder. So you can't pick something that you can't integrate eventually. So it might be something to integrate to begin with, but then it might turn into some new function that kind of messes you up. And there's some variations of this that we could look at, but let's do one more. Okay, I think we got time to do another one. So let's see here. Let's just do another silly one. Maybe a little bit longer or a little bit easier. But let's say we want to integrate x to the 6th, and then let's say, once again, well, let's use e to the x, because that's pretty easy to work with. That won't give us any grief here. But we will come up with a u and a dv. And the u that makes sense to get rid of is x to the 6th, and the dv would be the e to the x dx. So I've got a u and a dv column. Now, while taking the derivative and the integral of e to the x is easy, if you switched them and made the dv x to the 6th, it would get larger and never stop. So you would get something that would work, but it would be infinite and you couldn't write it. So let's just see here. Let's make this table. So u is x to the 6th, so that would be 6x to the 5th. That would be 30x to the 4th, 120x cubed, 360x squared, 720x. Let's slide up a little bit. And 720, and then 0. Okay, so that's very long. And if you were doing the long formula for integration by parts, you would probably get lost in keeping track of everything and maintaining the negatives that will distribute through. But on the dv side, it's e to the x. When you integrate it, it's e to the x every time. I mean, I just pulled this because it was an easy thing to work with. So we can take every diagonal. Let's see if I can circle them correctly. Because every diagonal is a u and the integration of the dv, so it's a uv. It helps when you have lines on your paper. But here is all the terms, and each term is going to alternate in sign. So positive, negative, positive, negative. So when you label those out, you always start with positive. But let's see here. If I got enough room to come back up. There we go. We might have to come back down and grab some things, but I think we'll run out of room either way. So the first term of this will be x to the 6th e to the x, and then minus 6x to the 5th e to the x. I'm a little bit messy. And then plus 30x to the 4th e to the x, minus 120x cubed e to the x, plus 360x squared e to the x, minus 720x e to the x, plus 720 e to the x, and the next one would be 0, I believe. And if we're talking about a definite integral, we could say plus c at the end. So let me pull it back down. But here we have the complete statement. The integral, or the integration of x to the 6th e to the x is 1, 2, 3, 4, 5, 6, 7 terms and a constant. And that would be a lot of work using the formal definition of integration by parts. But if we use this, which is called tabular integration, it will go much quicker. Now that tabular integration is integration by parts, but we just have a cool name for it. And there's some variations for how the table will work that I can make some other videos for as we move along. All right, but just to give you an idea of how the table works.